Welcome to the Remaro and Ease Fall School on Cognition-Enabled Robotics. And I want to start a little bit giving the big picture. And so when we are talking about cognitively enabled robotics, we should first think about what is a robot. And a robot is an electromechanical device. It's composed of links. Links are connected by joints. And for the joints, we have actuators that enable the robot to kind of move a link with respect to the previous link in the chain. And robots are equipped with programs. And the effect of the program, running the programs, is that the body of the robot moves. And these programs generally have a purpose, namely to accomplish tasks. And in many, many cases, accomplishing the task means changing the physical world, such as opening a fridge, getting objects out of that, and so on. So we are designing robot control programs and implement them in order to achieve, in the general case, underdetermined manipulation requests. So underdetermined manipulation requests can be something like clean up the kitchen, clean up the desk. But it can also be, for underwater robotics, something like inspect the pipeline or monitor an ecosystem on the floor of the ocean, or kind of repair an oil platform, parts of that. So it's always kind of tasks that have to be accomplished. And if we are talking about intelligent robots, the tasks are in most cases underdetermined, kind of vague, and they are formulated for an open world, so we don't know all the instances of the task we want the robot to accomplish when we are designing the programs. So what the control program has to do, it has to take underdetermined manipulation task requests and map them in a specific body motion that achieves the desired effects and avoid unwanted ones. So if we kind of ask the robot to set the table, we want at the end to have a completely set up table, and we don't want the robot to make a mess and kind of break things while doing so. And that's, of course, kind of an incredibly challenging task. But if we basically take humans and give them control over robotic devices, tasks like clean up the living room are perfectly manageable, right? So we see here a human remote controlling a robot to clean the table. And we see that kind of a robot can do so. So what that means for us as researchers in robot control is that a key problem in running intelligent robots is the software, right? So we are, of course, not there yet that we can basically clean a living room environment in the way kind of we have seen it right now. So if you see the most advanced of our demos that we are capable to do, it's actually nicely shown in this video. So let me show you.
Hi, my name is Gaia and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick-and-place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick-and-place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collected experience. For more information, please follow the links in the description below.
Yes, so in this fall school, we want to understand a little bit more what are the computing technologies that enable robots to accomplish tasks in this way. And you will have a number of hands-on exercises where you can basically look at part of the technology and do exercises in order to get more acquainted to these technologies. But if you're looking at mastering manipulation actions, it doesn't stop by doing something like setting the table, but the human capability of manipulating objects and performing physical tasks is much broader than this. So if we are looking at just one manipulation action, such as pouring, so the very cool thing about the human cognitive system is that humans can pour almost any substance from any source to any target and for any purpose, right? So, and I think we can basically watch videos from instruction videos from web pages such as WikiHow and take the demonstrations and translate what we see in the video to our own environments, to the tools, and accomplish the task successfully. So that enables us to pour not only from a bottle into a glass, but to perform other pouring tasks like pouring pancakes, kind of pouring water out of a noodle pot. But there are also much more complicated pouring tasks like neutralizing the acid, extinguish fire, water the plants. It's needless to say, if we want to have robots that are kind of assistant robots in our daily life, that they have to master some substantial subset of these manipulation tasks autonomously. So this is not surprising, right, that this task is so complicated, because if we are looking at the cognitive development of the human brain, one of the main purposes we have our brains is accomplishing these manipulation tasks successfully. And if you see you see here different animals and humans performing different motion tasks. And I think it's very clear that part of these motion tasks can be accomplished by data-intensive learning methods. But it's also clear that the goal-directed manipulation of action is a barrier in these capabilities, which is huge, right? And if we are looking at the cognitive development of the human brain, when it came to goal-directed object manipulation, the brain had to learn to use tools. Language was evolutionary developed in the same time frame. And it's clear that these different cognitive capabilities are not separate cognitive capabilities, but that they co-evolved. And they co-evolved in order to get that capability of acting successfully in the physical world. So in computer science, when you see a specific field of computer science did a huge jump in performance in a very short time. So that that's an idea pushed by Pedro Domingos. This was often due to computer science fields developing interface layers. So like the database systems, they developed an interface layer which is called relational database systems. And the relational database systems interface layer allows us to consider databases as tables of relations and combine them. That means that because we had relational database systems, we could separate the way we are implementing database systems from the way we are using database systems. And everybody knows that that made a huge push on database technology, right? The same happens with a hardware, software, that we have virtual machines and with high-level programming languages that abstract away from the von Neumann machine and allow to do application programming in more powerful mechanisms. So the question is, can we find a similar interface layer for cognitively enabled robotics, and in particular one that allows goal-directed object manipulation? And we are basically looking into that, and we are looking at the components of such an interface layer: the perception, the knowledge representation, and reasoning. And we go through that in this fall school. So, but what could be that very important idea that an interface layer for cognition-enabled robotics brings to the game? And from my point of view, I think it's a very old idea. So I was digging out. I had the pleasure of being a teaching assistant for the introduction to computer science at Yale University. That was about 30 years ago. But I think at that point, probably that slide was already 15 years old, right? And so one of the very first things that computer science students are told is that developing computer programs is getting an idea of how to solve problems, right? Expressing that idea in a precise and concrete language, which is a computer program, which has a precise semantics and gets the computer to solve problems by making the instructions of the computer program operational. But at the same time, so this is not kind of a one-way thing, but it's very important that the computer program is also communicating the idea of how to solve the problem back to the designers. And the reason is that kind of ideas can change, ideas can generalize, ideas can enlarge, and they can be very complicated. So if we are looking at kind of these examples I've given before about what cognitive manipulation involves, we see that these are the key challenges that nature had to solve in order to be able to master everyday manipulation. And what you are told in computer science or taught in the very first lecture is that the real concern of computer science is how to build large programs that can evolve and are stable when they are evolved, and that can effectively control complexity. And the methods, that's kind of what you're learning 2 lectures later, are kind of abstraction, and abstraction in 2 dimensions. So for one thing, the control abstractions and the data abstraction. And kind of another big idea is that you can take parts of programs, you can compose them. So you want to kind of compose your program from modular, reusable components with defined interface. So I think it's very natural that if we want to look at robots that have these capabilities, that we want to kind of go that way. And the way we are doing that, and that's also the framework of thinking for this fall school, is that the way we are going from underdetermined manipulation task to the specific body motion that achieves the desired effects and avoid unwanted ones is that we are designing generalized action plans for a particular category of actions, such as boring, that we will provide kind of templates of motion plans that these generalized plans can be translated to. And the means of kind of going from the generalized action plans to the concrete motion plan is contextualizing generalized description of how to move into concrete ones by applying knowledge and reasoning. So that's kind of the game that we want to play. So just briefly go through the components. So generalized plan, in particular the one we have seen in the video, it's kind of very compact. It says fetching an object and putting it at a particular location. So the robot just has to be at the location where the object is and perform kind of a fetching action on the object that should be fetched and placed. And at the destination, it should place the object at the right destination. So this is very compact because we are doing a lot of hand waving, right? We don't exactly spell out how the different motions have to be accomplished, but we just say kind of vaguely what has to be done. So the motion template is that we are kind of structuring the motion of robots into kind of hierarchically decomposed models. So for instance, for manipulation actions, it consists of reaching for the object, lifting it, transporting it, relieving it. And each of these phases has a goal. So if we reach for an object, we want to have the hand being in contact with the object, lifting it, the object being lifted on. And for each of these phases, we have particular parameters that tell us exactly how the motion should be executed. If we do reaching, we have to tell basically where and how the object should be grasped, which arm to use, and what is the reach pose, and so on. And how these programs look, this is, of course, kind of a subject in cognitive psychology, where researchers studying action science basically give us insights on how manipulation actions are structured. And this is actually what we condense in a pattern of motion plan. And we also see in the lower picture here on the left that if we are looking at fetching and placing tasks, they are very stereotypical, and kind of the structure is similar for all of them. So if basically in our control program we have these generalized action plans, we have these very concrete motion plan, then it's clear what is intelligent agency, right? So because it can only be one thing, right? So it's basically kind of answering the so-called body motion query. So what are the parameters, the concrete parameters in my motion plans? So like the location at which to fetch an object, the arm to be used, the grasp pose, lift pose, and so on, that I have to choose in order to perform the general action plan for that task request successfully, right? And the reason that kind of this is such a complicated reasoning task is that we want to find concrete parameters that imply the successful accomplishment of a very complex and underdetermined kind of task request. So the basic idea, the basic game that we are playing is that we believe that in the knowledge lies the power. So we are taking our generalized plan and we combine it with a knowledge base. And the knowledge base is a collection of knowledge items. And the knowledge items should be general. So they should be things like cups used for table setting have to be clean and unused. Cups in cupboards are usually clean. Cups have to be grasped outside. Then there can be much more general and powerful kind of knowledge pieces. Something like you should always parameterize your motions to avoid unwanted side effects. Spilling is an unwanted side effect of pouring. And so combining that and basically projecting how you you intend to execute your action will basically allow a robot to forestall kind of spilling failures. Yeah. Or we can have other pieces of knowledge like the pose of a robot that allows the robot to pick up a heavy pot, which is something that has to be learned from experience. So the game is that we have one single generalized control program. We want to have a huge knowledge base, and that knowledge base should allow to generalize that action plan to a huge variety of tasks, a huge variety of objects, a huge environment, a huge variety of environments and robots, right? And not only to these single instances, but the combination of all of them. So in this light, cognitively enabled robotics is about tasks, about robot body motions, and the physical effects of them. We are not kind of, in the programs, we are not touching kind of the body motions and effects directly, but we are developing models which are targeted at the tasks, body motions, and effects. And we want to represent basically these models of these tasks so that we can have computer programs that can manipulate these representations in order to perform their tasks. And therefore, we want to kind of think about what are the reasoning and the learning methods that are enabled by these representations of the models of the tasks, body motion, and effects. And all of these computation mechanisms have a single purpose, and that single purpose is to act successfully in the physical world. So cognitively enabled robotics is about acting successfully in the physical world through reasoning and learning methods that are enabled by representations of models that are targeted at tasks and body motions and effects. Okay, so let's start with the representation and reasoning part of it. So one powerful idea that artificial intelligence has created is that idea of physical simple systems, right? So that we can have computation systems that use explicitly represented symbol structure and processes that produce, destroy, and modify these symbol structures. And kind of these symbol structures, they, for one thing, designate objects in the world, but also processes which can be kind of the physical processes like picking up an object and placing it, but also mental activities that control other processes. And this idea of physical simple systems is kind of an incredibly powerful one, in particular if you are interested in kind of generalizing your ideas, if you want to basically transfer existing solutions to novel task instances and transfer it to other domains. So one of the most widely used kind of representational framework for physical symbol system is that idea of a logic. And the logic is not only a kind of a construct in mathematics, but it's a tool in AI for problem solving. And that tool consists of three components: the syntax, the semantics, and the calculus. The syntax basically specifies how we can encode information. So you all know predicate logic. So the mechanisms are that you can, for instance, in this situation here, you can say that an object called cooking pot is in a place which is the right shelf, and the relation that is true for these two entities is the relation on. And we can take these statements that we have and combine them to more kind of complex expressions. So we can say not only that the cooking pot is in the right shelf, but we can also say that the popcorn is also in the cooking pot. And we can have other mechanisms of creating more complex statements about the world, something saying like, each cooking pot is a container. The second component is the semantics. So logic allows us to give basically each of these expressions a meaning, which means we can say that this expression is true or false. And the third component, that's kind of what we had with the simple system, is that the logic also provides us a way of manipulating these objects. So the semantics, we already talked a bit about it. So it's basically the names in the symbolic expressions refer to entities in the world. The relations are the predicates denote relations in the real world, like being on top of something. And basically, an expression has a value true if the object denoted by cooking pot 3 is on top of the entity denoted by right shelf here. Then we can basically define the semantics of more complex expressions, like a more complex expression like the expression in corn cooking pot and on cooking pot right shelf. This expression is true if both of the components are true. And something like for all x, cooking pot x, container x is true if for each instance in our world, if this is true cooking pot, then it's also container. The calculus is essentially kind of a way of manipulating objects, symbolic expressions. So if in our current symbolic knowledge base, we have the expression like cooking pot or 3, and we have the expression that each cooking pot is a container, we can add to the knowledge base a new symbolic expression, namely that cooking pot or 3 is also a container. So what the calculus gives us is a way of, in the case of logic, of adding new symbolic structures to the knowledge base. And in particular, we are interested in the case of logics that the new symbolic expression that we are adding is true if basically the constituents for the reasoning step are also true. So this is kind of very important that we are designing logics where the semantics and the calculus have kind of two important relations with respect to each other, which means, so for one thing, if we perform a computation of in simple manipulation operation, if we execute the simple manipulation operation on expressions that are true, then basically the output should be true. That's kind of the correctness of the simple manipulation object. The other thing is that we also want to have our simple manipulation mechanism that it's complete. So that means that every symbolic expression that is true can also be derived from the symbolic expressions, right? And that's kind of a very, very important relationship between the two of them. And the reason is that this enables us to solve problems automatically without our computer systems having to understand what they are manipulating, right? So if we want to, in this setting where we have a calculus which is correct and complete, we want to know whether a particular statement is true, we can simply take our knowledge base and kind of explore the set of all simple structures that can be kind of involved from that knowledge base. And if the symbolic structure in question is in the transitive closure of the simple manipulation, then we can basically infer that this is also a true statement that is represented by the simple structure. And that's very cool, right? Because then actually doing meaningful inferences in some domain comes down to blindly search on all possible simple manipulation structures, right? Okay, then we want to basically apply that to robotics, right? So we want to basically build a knowledge base that axiomatizes robot agency. And the question is, can we build a knowledge base of axioms about robot agency? So that is basically having generalized statements about what is true that is sufficient for answering the body motion query for some non-trivial task domain, something like making popcorn, right? And so we will basically look a bit more into that. But the reason that kind of doing that using knowledge representation and reasoning mechanisms is that if we are looking at what is happening in knowledge representation and reasoning, we now see a lot of extremely powerful tools for automating knowledge-based construction. So we see huge ontologies or encyclopedias that are useful for autonomous robotics. So examples are Wikipedia and Wikidata. We can see knowledge graphs like the Google knowledge graph, right? So if we are looking just at subgraphs of that knowledge graph, something like OpenStreetMap, we can see that a knowledge graph having the content of OpenStreetMaps would help our outdoor robots to navigate to the right places, right? So we can also look at the experience data or the log files that robots collect and use them for acquiring knowledge, or kind of we can ask humans to play games like showing how to solve manipulation tasks in a virtual reality environment and learn from that. And of course, what we want to have at the end is we want to have a knowledge service, web knowledge service for robots, just like the Siri agent or Amazon Alexa, that robots can ask on how can I accomplish a particular task. There are also issues in representations. So we also have to think about how to represent and reason with uncertain information, with physical change. Kind of in many frameworks, skills and procedural knowledge is completely differently represented from declarative knowledge about the ways. And also it turned out in the last years that artificial memory structures are very important forms of organizing knowledge. So let's have a look at a concrete example. So we want to basically look at popcorn making. So the question is, can we basically represent robot activity like popcorn making in terms of logic knowledge bases, and what have researchers in that area done in order to kind of solve these reasoning tasks? Okay. So the standard model, if you are kind of attending the Introduction to Artificial Intelligence and Russell Norvig, is that you model kind of problem solving as the interaction of an agent with its environment. So you typically kind of these two things interact with each other, that the agent perceives the environment, kind of the perception of the environment gets translated into symbolic structures. Then we have the so-called agent function that maps the history of percepts into the next action that the robot should execute in this situation. And that action gets translated by the motion controller in a body motion and kind of changes the environment. To see in this framework, we are observing how the environment changes. we are basically looking at discrete time steps, where basically the succeeding time step or the state at the succeeding time step is always the state at the previous time step plus the effect of the body motions of executing an action R. And we are basically looking at that sequence of state transitions, apply objective functions, and the purpose is to find an agent function that optimizes this objective function. The model of the environment is typically extremely coarse-grained. So if you are looking at popcorn, so typical kind of representation is this. So we have kind of very few places like left tabletop, right tabletop drawer, and the model of the system is a state transition system with atomic state transitions. So you basically, when going from this state to this state, it's basically taking kind of the bowl and placing it here. These actions are modeled in languages such as PDDL. So we have an action fetch and place that we have talked about before. And we typically represent it in terms of preconditions so that the object is at the from location at the beginning of the action execution. The robot has to have an empty hand. And if the fetch and place action is successfully executed, then the location of the object is a to location and the hand is kind of empty again. So if we are looking at that, it basically turns out that we have a very abstract representation of the of actions, which basically say what actions do, but this specification does not tell us how actions are executed. And this is kind of, if we are looking at this from a robotics perspective, a very big limitation, right? So, because if we are looking at one pouring action, such as pouring water out of this pot, a robot can only execute that action robustly if it basically infers that it has to grasp the pot by the handles, that it has to hold the pot horizontally, that it has to tilt the pot around the axis between the handles, and it has to hold the lid while pouring. If we are looking back in our action models, so none of this information is contained in these action representations, which means that these models that we are looking at, they are not sufficient for controlling robots effectively in the real world. And how we get better representations about the environment, about actions that help us to actually infer these pieces of information, we will hear in the next lecture. Thanks for listening.